I want to give an overall review to this lecture. So initially, I introduced the concept of a Smith chart. So basically, a Smith chart is a family of curves on the gamma plane in the polar coordinate system. And every point on this chart is a gamma value subject to some low resistance and low reactance. And for example, if you have a value for RL, then you can plot the gamma value on those black circles. If you give a value for XL, then you can plot those gamma values on the blue circles. And for a given transmission line, the gamma L on this Smith chart is a circle, and we call this the standing wave ratio circle. And the radius of this circle is a constant because on a given transmission line, the magnitude of the gamma is already fixed. And if you want to find the reflection coefficient, including the phase, from a low impedance, then you identify the value of the low impedance on this Smith chart. And then draw the standing wave ratio circle. The radius of this circle is going to give you the magnitude of the reflection coefficient. And the phase angle is measured from this real line, real axis to this green line. The total length of this circle corresponds to 2 pi phase shift, but it also corresponds to the length of the transmission line. So if we equate this 2 beta L equal to 2 pi, then you can find that the total length for one revolution of the standing wave ratio circle is equal to half wavelength. This means that you can move this low point along this SWR circle over some distance, and then the distance can be converted into a length with a unit of the wavelength. And if you move a whole circle, then it means that you will be moving over a length of half wavelength. So this is a little bit cartoon tell you the situation. And in terms of measuring the length, the starting point is usually here. So this 0 means that the starting point of the reference point, the starting point as a reference for the line. And if you move a whole circle, then the total length will go over the 0.5 wavelength. So this point corresponds to a length of 0.25 wavelength with reference to this point. But in terms of angle, we always define the 0 point on the real axis, on the positive part of the real axis. So at this point, the phase angle is 0. And because the z is defined to be at certain location of minus L, so we put a minus sign in front of this phase angle. So if you walk toward your generator, then you'll be doing clockwise motion on this circle. And so the clockwise rotation corresponds to moving toward the generator, because again, the definition of the z is equal to minus L when you walk over toward the generator. So we'll be dealing with the negative phase angle. So the angle is moving down in the clockwise direction. And if you want to transform the low impedance to some input impedance at location of z equal to minus L, you rotate this low impedance point along this standing wave ratio circle to some length. Then you read the value of RL and XL to determine the input impedance at this point. And given a a standing wave ratio on the line, the locations of the maxima signal and minima signal are on the real axis. So when you move on the standing wave ratio circle and you hit this negative plot of the real axis, then this will be the location of the minima voltage. But if you continue to move on this line and hit this positive plot of the real axis, then you will be measuring a maxima voltage at this point. And I want to point out again, the location of the maxima voltage will correspond to the locations of the minima current. And I also talk about how to read the standing wave ratio on this Smith chart. And it turns out that the standing wave ratio of a transmission line is just the RL value on the positive plot of the real axis. And then we talk about admittance, because we talk a lot about parallel connection of the transmission line to other transmission line. So it will be easier to work with the admittance. So it will be convenient if a Smith chart can also offer the solutions of admittance. And indeed, if we just rotate the point of the impedance by 180 degrees, then the value of the RL and XL at this point will give you the value of the normalized admittance. And then now we are in the position to connect parallel lines to a main line to cancel out the reflection. So the idea is that you identify a small section of the length on the main line and connect a proper length of the parallel line to it. And then you end up having the total admittance equal to the characteristic admittance. Then you can cancel out this reflection. And it's most convenient to have a short circuit line or an open circuit line, because either line can provide you any value of the admittance or impedance, provided that you properly decide this length so that you accomplish this y in equal to y0. And so the last point basically tells you this concept that it's very convenient that you just use the short circuit or open circuit line to do this impedance matching or admittance matching. Thank you very much, and this is the end of my lecture here.